Hi everyone, my name is Advit, and my senior project is about touchless typing using a time-of-flight depth sensor and OpenARK, an open-source augmented reality software kit to track finger position and determine key presses. My internal advisor is Ms. Bhattacharya, and my external advisor is Dr. Alan Yang from UC Berkeley Center for Enhanced Reality. So we begin with the past, and to start us off, here's a clip from The Office.
I know a lot of us have been feeling under the weather lately. It's that time of year. And according to a study done by the University of Arizona, they discovered that your keyboards have hundreds of times more bacteria per square inch than a toilet seat.
I heard your mama has more bacteria.
So we're gonna ignore the rest of that clip.
I know a
But
lot.
yes, as mentioned by the lady in the video, Pam, traditional human interface devices such as keyboards and mice are dangerously unhygienic. This is harmful especially given the current pandemic we're living in, with physical touch allowing for the spread of germs and contaminants. Additionally, these traditional human interface devices are bulky, not readily portable, and restrictive in terms of usage. They've been proven to lead to repetitive stress injuries and require users' hands to remain in the same position every time. Such problems have given rise to the field of touchless technology. The way these devices generally work is by using a sensor to determine the user's fingertip positions, mapping them to the user's screen, and using a change in depth to determine key presses. Yet, these solutions aren't exactly the most ready to be used, so let's take a look at a few of them to see exactly why. The first solution we'll look at is touchless typing using head movement-based gestures. And although the solution boasts a high accuracy rate, the reason for this is because of its use of multiple cameras, as shown in the red boxes over here on the left, and that it requires users to look at the keys they want to press. As a result, the solution is restrictive and not portable. Wearable gloves or bands like AirType and TapStrap 2 are not touchless. Because they're user-specific, they can't be implemented in public places or for multi-user scenarios. It requires users to carry around gloves, which may require washing and suffer from more wear and tear than a single camera. Next, we have Titan, typing in thin air naturally. The problem with this solution is that it utilizes two front-facing depth cameras, namely the Leap Motion Controller and the Xbox 360 Kinect. Now, what's the issue with these? Well, the Leap utilizes two stereo cameras to calculate depth, which requires more compute power. Additionally, it has to be mounted underneath the user, preventing it from being movable. As a result, this system simply isn't portable. Additionally, the Xbox 360 Kinect sensor is meant more for full-body detection, as seen with the game Just Dance, and is not accurate enough and too large to be readily portable. Even more of a problem is that the Xbox Kinect sensor has been discontinued by Microsoft. So in all of these solutions, there are several drawbacks that prevent them from truly replacing traditional computer keyboards and mice. Put simply, there's a reason they're not widely used today. My project is aimed towards making gesture-based keyboard control more efficient, portable, and easy to use. Now, how exactly will we make a more efficient gesture-based keyboard? Well, it starts with the hardware. First, we will use a time-of-flight sensor, which emits and measures reflected infrared light to generate a depth map of the user's environments. This is the Intel D435i, the desk camera I'm using. The reason for this is its built-in IMU. An inertial measurement unit is a small device that measures acceleration, tilt, and relative velocity and position of the camera. Because of its built-in sensors, we can use a SLAM algorithm to map out the user's environment to calculate the true position of the user's fingers, even if the camera moves. Therefore, the camera doesn't have to be fixed mounted and can even be attached to a pair of wearable smart glasses like the Google Glasses, for example. So next, we dive into the software. This system needs to run in real time, otherwise it's going to be slow, laggy, and unusable. To help speed up processing time and divide this complicated system into smaller substeps, I utilize multi-threading. This splits up work into different threads, allowing them to work concurrently. The two main threads utilized here were a main thread, which interfaces with the camera and is in charge of detecting fingertips, and the keyboard thread, which is in charge of updating the GUI and making clicks. So we'll start with the camera thread. In order to interface or receive and process data from the Intel D435i desk camera, I utilize the OpenARK library. OpenARK is an open-sourced augmented reality software development kit that I've been working with since my internship with UC Berkeley's Professor Yang in the summer. Although I'd love to share more about my internship and the origins of this project, we simply don't have the time for that right now, so feel free to ask more about it during Q&A. Continuing on with OpenARK, by upgrading its hand detection feature, I was able to accurately track both of the user's hands and all 10 of the user's fingers individually. Pretty neat. However, the path to get here wasn't easy. First, I needed to ensure that regardless of the number of fingers detected, the program still continued to function. As shown in this video, the system can work with any number of fingers detected. So there's 2 fingers now, and then you increase it to 3 fingers, and then finally all 5 fingers. Next, the issue became determining which finger was which. One problem I constantly faced was flip-flopping, especially for the pointer, middle, ring, and pinky. It was hard to distinguish which finger was which. And some frames would say, this is my pointer finger, and others would say, no, this is the pointer finger. And to overcome this, I implemented an algorithm using vectors. I calculated the angle between the vector from the wrist to the palm and the vector from palm to the finger. And then I established several thresholds for which angle corresponds to which finger. So for example, your thumb roughly makes a 50-degree angle with your wrist. So here, around 50 degrees, and your pointer is roughly parallel, so just a straight line up. And after some fine tuning, it could detect which finger was which. So here I'm showing it my pointer finger, and then I switch over to my thumb, switch over to my pinky, and then so on and so forth. Now that the main components of the camera thread have been wrapped up, we can move into the keyboard thread. To create the keyboard graphical user interface, I utilized OpenGL, a C++ library. I created a blank canvas at the bottom of the screen and initialized green keys representing the alphabet. Then I added a purple bar at the top to represent what the user has typed so far. In order to improve the user experience, I changed the colors of the keys depending on the state of the user's fingers. If a finger is hovering over a key, its color changes to yellow, shown in the bottom screenshot. And if a finger is currently pressing a key, as shown with the F, its color changes to orange, as seen in the top screenshot. Yet, the biggest hurdle in the keyboard thread was by far detecting clicks. My underlying algorithm stored the Z positions of each fingertip in a data structure, and if the change in Z positions for any fingertip was as follows, a key press was registered. So at the start and end of the click, the Z position should remain largely unchanged, and in the middle of the click, the depth should be significantly less or closer to the camera than at the start or the end. And the reason this was so tricky to nail down was due to the unexpected noise and fine-tuning for specific thresholds. The accuracy of the camera and the detector aren't things I can rely upon 100% of the time, so this failsafe helped allow for a more seamless experience. And all put together, the key presses look something like this shown here. So just by moving my finger in the air, I can type out words, and each letter that I press is shown over there in the purple bar. So I'm not going to say what word I typed, but it was adios. But yeah, pretty impressive. And finally, combining the key presses with all 10 fingers, we get full touchless typing. And I'm still working on debugging the 10 fingers a little bit, but I've seen it accurately detects all the fingers displayed, showing them on the screen. So you got the right hand and the left hand. And then I can just switch over to 2-finger typing and then type out words. And we don't have the time to type out a full word again, but I started typing out the first 2 letters of the word hello. So pretty impressive. And although it starred in some rather neat demo videos, this project is far from over. But first, some of the issues I faced along the journey. So this project was far more challenging than I initially expected. And here's an example of one of the biggest hurdles I faced, redundancy. At first, I was seeing a lot of redundant code. The same algorithm had to be utilized for each finger, and each finger had its data stored in new variables and arrays all over the place. As a result, I decided to create a class specifically for fingers. A class is a sort of blueprint for representing some abstract object. So in this case, the finger class would neatly store each finger's positions, ID number, label, whether it's being pressed down or not, which hand it belongs to, all in one place. And this helped dramatically reduce the amount of code needed to initialize fingers and help simplify my algorithms. So as seen in the top right image, that's what I need to do before, just to initialize 2 fingers only, just 2 fingers. And now, as seen in the bottom right image, that's it. That's all the lines I need just to initialize all 10 fingers. So as seen, I initialize 5 on one hand, 5 on the other hand, and then store them each in an array or in a list of each hand's 5 fingers. Yet, regardless, as seen in this video, this project evolved a lot more code and a lot more debugging than I initially expected. And here's just 3 of the main files. And I think the biggest reason for all this code is that there's just so many intricate moving parts. Detecting which hand is which, how many fingers are shown, which finger is which, creating a virtual keyboard, updating each fingertip position on the keyboard, changing its colors, detecting clicks, and on top of all this, there's still debugging. So there's a lot of things going on at the same time here, which is why it ended up being a lot more code than I expected. And however, there's still more to be done. And I intend to continue pursuing this project well into the summer. First of these steps is harnessing the power of the D435i's built-in IMU. By implementing an algorithm like simultaneous localization and mapping, or SLAM, the camera will be able to freely move. As of right now, I've just been testing with a stationary camera in order to get the prototype algorithm working, and after a freely moving camera has been finalized, I'll implement the system in smart glasses and design an embedded device. After this, it's just testing and revisions, and finally, I'll aim to deploy this system in public spaces such as kiosks and library computers. Now, this brings us to the final question of what's the point of all this? Well, the system has 4 key benefits. Number 1, it's more hygienic. This device can provide the full functionality of physical keyboards without requiring physical contact. Exacerbated especially by the COVID-19 pandemic, we realize how easy it is for germs to spread from person to person. As a result, for public shared devices, using this touchless system will prevent the spread of contaminants, making the usage more hygienic for all. Number 2, in comparison to other touchless typing implementations, this solution is more portable and efficient. It doesn't use optical or stereo cameras, allowing it to work in low light, low contrast situations, have a greater accuracy, and require less compute power. It only needs one sensor, making it small and portable. Because of its future IMU and SLAM implementation, the camera won't have to be fixed mounted, making it less restrictive. Number 3, allowing for more usage scenarios. For example, doctors can quickly reference the patient's medical history in the operating room without having to remove their gloves, wash their hands, then put on a new pair. And with the growing usage of augmented reality and virtual reality, entire computers could be stored in smart glasses and interacted with through this program instead of having to carry around bulky VR or physical controllers. And finally, it's healthy. Users who may suffer from repetitive stress injuries may be helped by this added flexibility. From an economic perspective, there's a longer lasting lifetime. Since users will not be touching the sensor, there'll be less wear and tear and no additional costs in cleaning the sensor, sanitizing it, or ensuring that there's no contaminants caught between the keys, which from personal experience, I know is a real pain. The current state of touchless technology is promising, yet requires more progress. There's a reason it isn't widely used today. By using one camera and inertial measurement unit, my senior project has been working towards making this technology more accessible and user-friendly. As demonstrated by several proof of concepts, this touchless system will work. It'll allow for more usage scenarios, for example, those with disabilities or perhaps with soiled fingers at the moment. It'll be far more hygienic in terms of less contamination. It'll be easier to carry and access. It'll be better for health in terms of RSIs and economically, and it'll provide a superior level of flexibility and customizability in terms of usage. As a hallmark of every sci-fi movie, this technology is indeed the future, a smarter form of human-computer interaction. everything will be at our fingertips, literally. So thanks for listening. And this is my bibliography. And any questions?